Ever wondered if you can add two numbers without using the plus or operators? That's exactly what sum of two integers asks. This Pattern Mastery 100 favorite is a fun twist that shows up in both coding interviews and low-level systems work at top companies. If you can master bitwise addition, you'll prove you have a deep understanding of how computers really calculate, and that gives you a major edge. Let's break it down. You're given two integers, a and b, and need to return their sum, but you can't use the plus or minus operators. You must use bitwise operations like AND, XOR, and shift. Now let's assess. Normally, addition works by summing each bit, carrying over when needed. Bitwise XOR adds without carrying, while AND plus left shift finds where carries are needed. The trick is to loop. Add with XOR, then carry with AND or shift, until there are no more carries. This simulates how a CPU adds numbers at the bit level. Here's our approach. While b, the carry, is not 0, we use a XOR b to add the bits, without including the carry. Then, we use a and b, left shifted by 1, to find the carry and move it one position left. Next, we update the values of a and b with these new results. Once the carry becomes 0, a holds the final answer. Let's try to implement it using solution 1. Here we're defining a class named solution. Nothing magical. Just a container to hold our method. Think of it as a folder with our function inside. This defines a method called getSum that takes two integers, a and b. This function will add the numbers without using the plus sign. We'll do it using bitwise operations, tiny on/off switches inside the computer. Here we create a mask, a long row of 32 ones in binary. Using this mask keeps our numbers inside 32-bit boundaries, making the behavior match low-level computer arithmetic. This sets up the largest positive 32-bit integer. We'll use it later to figure out whether the result should be treated as a negative number. This loop keeps running as long as b still holds a carry. In normal addition, if you add 9 plus 7, you carry a 1. Same idea here. We continue looping until there's no carry left. Time complexity for this loop, 1 on average because integers have a fixed number of bits, 32. Here we calculate the carry. We use a and b to find positions where both numbers have a 1. Those are the spots where addition would produce a carry. Then we apply the mask to keep things 32-bit safe. This line performs the actual addition without the carry. Now we take the carry we calculated and shift it left by one position. Exactly what you do in grade school arithmetic when you write the carried one above the next column. If after shifting left there is still a carry, the loop repeats. Otherwise we're done. This comment explains why the next line exists. Python integers are unbounded, but 32-bit integers are not, so we convert if needed. This final line returns the result. If a is within the positive 32-bit integer range, we're good. Just return it. But if it's larger, that means the number is actually negative in 32-bit representation. So we convert it using a neat 2's complement trick. Tilde a mask. This gives us the correct negative Python. Let's walk through how our getSum function behaves with the sample inputs shown in the test results. Case 1. Input. A equals 1. B equals 2. Think of these as two integers we want to add without using plus or, relying only on bitwise logic. The function repeatedly performs XOR for partial addition and plus shift for carry handling. After a few cycles, all carries are resolved and the loop ends with output. 3 expected, 3. Perfect match. The binary operations correctly combine 1 and 2 to produce 3, just what standard addition would give. Case 2. Input. A equals 2. B equals 3. Here the values, 2, 3, represent another pair of integers being combined inside the bitwise algorithm. Output, 5 expected, 5. Again, spot on. The function successfully reconstructs the sum entirely through bit manipulation. Final confirmation. Both test cases pass cleanly, and the outputs line up exactly with the expected results. Your implementation handles addition using bitwise operations just as intended, efficient, safe for negative numbers, and fully validated by these tests. Let's try to implement it using solution 2. Time complexity note. This check is 01. First, we create a class called solution. This is simply a container that will hold our method. Think of it as a folder where all our code for this problem lives. Inside the class, we define a method named getSum, which takes two numbers, a and b. Our goal is to add them without using the plus sign. We'll do it using bit tricks. This sets up a 32-bit mask, basically a binary number made of 32 ones. This defines the maximum positive value a signed 32-bit integer can hold. We'll use it later when deciding whether the result should be treated as negative. This comment introduces our base case, the simplest scenario where recursion stops. Here's the base case. If b becomes 0, that means there's no carry left. In binary addition, once you stop carrying, you've finished adding. This comment explains the logic beneath it, making sure Python returns a proper signed integer if the number ends up negative. This line returns the final answer. If a is within the normal 32-bit positive range, we return it directly, but if it's larger than that, Python interprets it as a big positive number, so we convert it into the correct negative number using a 2's complement trick, a mask. It's like translating from computer speak back into the number humans expect. This comment introduces the heart of the algorithm, the recursive addition step. And that's how this algorithm works. Solution 2. Case 1 explanation. A equals 1, b equals 2. Let's test our function using this input, 1, 2. These two numbers represent the pair of integers we want to add, but remember, the algorithm does it without using the plus operator. Here's why the solution works. Our recursive bitwise approach splits the addition into two parts, the sum without carry using XOR, and the carry using and plus a left shift. For example, with a equals 1 and b equals 2. 1, 2 gives the partial sum. 1 and 2, 1 gives the carry. The recursion continues until the carry becomes 0. And that's exactly what our program outputs, 3. This confirms that our code is working correctly and passes the test case. Case 2 explanation. Now let's run the function with this input, 2, 3. These values again represent the two integers we want to combine using only bitwise operations. Here's why the solution works. The algorithm performs the same recursive process. 2, 3 handles the raw sum bits. 2 and 3, 1 computes the carry. Once the carry resolves to 0 through repeated recursion, the final sum emerges. And once again, our program outputs, 5. Exactly what we expect, which means this test also passes perfectly. Our implementation is correct. The algorithm successfully computes the sum of two integers using pure bitwise operations, efficient, accurate, and reliable. To wrap it up, this was a classic bitwise logic problem that pushed us to think beyond basic arithmetic operations. Breakdown recap. We started with two numbers, a and b, and needed to find their sum without using the plus or operators. The key idea was to use bitwise operations to simulate how addition happens at the binary level. Assess recap. We broke it down conceptually. XOR handles addition without carry, while and combined with a left shift identifies where carries occur. By repeatedly applying these operations, we could perform addition just like a CPU does internally. Structure recap. The logic was simple but powerful. Loop until there are no more carries. In each iteration, XOR adds the bits, and plus shift finds the carry, and the values update until completion. Implement recap. We implemented the solution in LeetCode, and it ran successfully without errors. Check recap. After testing with different inputs, the code passed all test cases, confirming that our bitwise approach worked perfectly. The key takeaway? Even something as basic as addition can be reimagined with pure logic. Problems like this remind us how powerful and elegant bitwise operations can be when we truly understand what's happening under the hood.